Hi everybody. So today we are going to talk about Schrödinger's equation, which is the basic equation of motion that describes how quantum systems evolve. Before we get there, let's talk a little bit about observables. So what's an observable? It's a quantity like energy or position or spin, something that you can measure. And okay, so what do we mean by this? Well, there's some quantum state that we have, and we feed it into our measuring apparatus, and the measuring apparatus has a meter. If it's an old-fashioned measuring apparatus, it has a meter which it has a needle where the needle deflects, and so the deflection of the needle is some real number. It's labeled by a real number, and so an observable is our operator that tells us, given this quantum state, what the real number is. Okay, so more precisely, suppose that we are working with a k-level system, so that our quantum state is a unit vector in a k-dimensional complex vector space, a Hilbert space. Then the observable for the system is an operator A, which is a k by k Hermitian matrix. Right? Remember, Hermitian matrix is a complex matrix such that A equal to A conjugate transpose, A equal to A dagger. So for example, if k equal to 2, then we might have the following Hermitian matrix. So the diagonal must be real, so it might be 1 minus 2, and then this entry is the conjugate of that. Okay, but you might be a bit puzzled now, because then we already have a notion of measurement. So if you wanted to measure a quantum state, we just picked an orthonormal basis, phi 1 through phi k, and then the corresponding outcomes would be 1 through k. Sorry, you can number them phi 0 through phi k minus 1, and the outcome 0 through k minus 1. It's sort of an arbitrary choice. Okay, but that's what we said a measurement was. So what's this new notion of an observable? Okay, so how can it be that a measurement now corresponds to this Hermitian matrix? Well, so let's just think back. What's special about a Hermitian matrix? A Hermitian matrix is special because there's the spectral theorem. So if A is Hermitian, then it has an orthonormal set of eigenvectors, phi 1 through phi k, with real eigenvalues lambda 1 through lambda k. What this means is A times phi I is lambda I times phi I. Okay, so now what does it mean to use this observable to do a measurement? Well, all it means is that if we write our state psi in the eigenbasis, phi 1 through phi k, then the measurement outcome is going to be lambda I with probability the square of the magnitude of the ith component of psi. And the new state is just phi I. Okay, so let's step back and understand what this is saying. So what we're saying is, when you specify a Hermitian operator A, a Hermitian matrix A, you're really specifying an orthonormal basis. Which orthonormal basis? The orthonormal basis of the eigenvectors of A. But now, not only do you get this orthonormal basis, but you also get corresponding real numbers, which are the eigenvalues. So what does it mean when we do a measurement according to A? Well, what we are saying is A specifies an orthonormal basis, which is phi 1, phi 2 through phi sub k. Okay, that's once we write down A, we've specified an orthonormal basis. Now if our quantum state was psi, what happens when we do this measurement? Well, psi gets projected onto one of these, the measurement basis states. So if it happens to be phi sub I, well, then the new state is phi sub I. But what do we actually read out in our measurement? Well, before we were saying we read out I, but really what we read out is lambda sub I. So if the measurement outcome was phi sub 2, then our meter would show a deflection of lambda sub 2, which is a real number. Okay, so those are the rules of measurement. So for example, if our state was alpha 0 plus beta 1, it's a qubit, and suppose our observable is x, which is a bit flip. Now remember the eigenvectors of x. So the eigenvectors are, let's call them phi 1 equal to the plus state and phi 2 equal to the minus state. And the corresponding eigenvalues, lambda 1 is equal to plus 1 and lambda 2 equal to minus 1. Okay, so now we want to understand what happens when we do a measurement. So when we measure, we need to write down the state psi in this eigenbasis. So if you write it in the eigenbasis, you can sort of work this out. It's I believe it's alpha plus beta over square root 2 plus alpha minus beta over square root 2 minus, just to a change of basis. And so now the outcome of the measurement is plus 1 with probability alpha plus beta over square root 2 magnitude squared. And if so, the new state is just plus, and it's minus 1 with probability alpha minus beta over square root 2 magnitude squared, and then the new state is minus. We could also ask, what's the expected value of the outcome? Well, if it's 1 plus 1 with this probability minus 1 with this probability, the expected value of the outcome of the measurement is just 1 times alpha plus beta over square root 2 squared plus minus 1 times alpha minus beta over square root 2 magnitude squared. Okay. Okay. Now there's something that what I said so far was not entirely correct, and the reason it's not entirely correct is because we do have to worry about repeated eigenvalues. So let's take this three-dimensional example. So let's say that we have an observable and it has these eigenvectors phi 1, phi 2, phi 3. But suppose lambda 1 equal to lambda 2 equal to 1, right? So now you could ask, what happens if the measurement outcome is 1? Is the new state phi 1 or phi 2? Right? Well, okay, so here's the correct picture. You see, the spectral theorem really tells us that, okay, so in the case that there are repeated eigenvalues like lambda 1 equal to lambda 2, then in fact you can find this orthonormal basis. Phi 1 and phi 2 are definitely eigenvectors, but actually any vector in the space spanned by phi 1 and phi 2 is also an eigenvector with eigenvalue 1. So for example, if you took 1 over square root 2 phi 1 plus 1 over square root 2 phi 2, you can check that this is also an eigenvector with eigenvalue exactly 1. Why? Because if you hit it with A, Well, a times phi1 is phi1 and a times phi2 is phi2, so you'll just get back 1 over square root 2 times phi1 plus 1 over square root 2 times phi2. And of course you can see that this would hold for any linear combination of phi1 and phi2. Okay, so you know, the fact that we singled out phi1 and phi2 is completely artificial. In fact, it's the whole eigenspace, the entire eigenspace with eigenvalue 1. So the outcome of this measurement would be, well, it's either 1 or 2, and if the outcome is 1, then the new state is just the state psi projected onto this eigenspace. Right? So you project it into this plane. Okay? And what's the probability that you'll get this outcome? Well, you can figure out the probability either by working it out as the, if alpha1 is the amplitude in this direction phi1, then it's going to be alpha1 magnitude squared plus alpha2 magnitude squared. Or you could use Pythagoras theorem and you could say directly the probability that you'll get this outcome is just the square of this projection. So it's this length squared.